Have you ever wondered why we exist? Why are there sparkling stars, lush green planets, and you yourself, all made of matter? It might sound obvious, but our universe shouldn't be this way. According to the laws of physics we know, matter and antimatter were created in equal amounts during the Big Bang. So, what happened to all the antimatter? If everything was perfectly symmetrical, the universe would just be an empty sea of energy. But no, we are here, and the question, why does the universe have more matter, is one of cosmology's deepest mysteries. Let's explore matter's extraordinary journey to survival. Welcome to SpaceTime's universe journey of discovery, where we explore the deepest mysteries of the universe. In this video, we'll explore matter and antimatter. Why does the universe have more matter? Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us. To truly grasp this perplexing puzzle, we need to travel back in time to the incredibly brief and intense moments immediately after the Big Bang, when the universe was only a few billionths of a second old. At that time, the universe was not a cold, dark space, as it is today, but a superheated, dense, and chaotic plasma soup. Temperatures and energies were so high that fundamental particles were constantly being created and annihilated in an endless cycle. In this extreme environment, the laws of quantum physics allowed pure energy to transform into matter and antimatter according to Einstein's famous equation E equals mc squared. This means that whenever a matter particle was created, such as an electron, a corresponding antiparticle, in this case a positron or antielectron, also simultaneously appeared. Quarks, the building blocks of protons and neutrons, also have their antiquarks, each antiparticle carrying an opposite charge but the same mass as its matter counterpart. Matter and antimatter share a nearly perfect symmetrical relationship. They have the same mass, the same energy levels, and interact in the same ways with the universe's fundamental forces. The most obvious difference is electric charge. Electrons carry a negative charge, while positrons carry a positive charge. When a matter particle and its antiparticle meet, they don't just collide, they annihilate each other, completely transforming their mass back into pure energy, typically in the form of high-energy photons. This process is so efficient that it leaves no trace of the original matter or antimatter. In the early universe, this creation and annihilation process occurred with astonishing balance. Physics models indicate that matter and antimatter were born in almost exactly equal quantities. It is estimated that for every billion matter-antimatter pairs created, another billion pairs would find each other and annihilate. If this symmetry were absolutely perfect, then as the universe cooled to a certain threshold, the process of new particle creation from energy would cease. Afterward, all remaining matter and antimatter particles would continue to seek their partners and annihilate until nothing was left but a sea of photons. But our universe is not an empty sea of energy. On the contrary, it is teeming with matter. Colossal stars, galaxies containing billions of stars, planets, and ourselves. The almost complete absence of antimatter on macroscopic scales, except for small amounts produced in high-energy reactions or in laboratories, is irrefutable evidence. This confirms that there was a small but decisive imbalance in the very first moments of time. Scientists have deduced that for us to exist in the early universe, there must have been an extremely tiny excess of matter compared to antimatter. A common analogy used to illustrate this is, for every billion matter-antimatter pairs, there was one single extra matter particle. It is that tiny one extra matter particle per billion pairs that after all the matter-antimatter pairs annihilated each other, remained to form all the stars, planets, and complex structures we observe today. This ratio is incredibly small, but it is the foundation for the existence of everything. To explain this mysterious cosmic asymmetry, the renowned physicist Andrei Sakharov proposed 3 fundamental conditions in 1967. These conditions, known as Sakharov conditions, are necessary for an excess of matter to form and persist in the early universe. Without any of these conditions, our universe likely could not have harbored life. The first condition is baryon number violation, B. Baryons are a type of heavy matter particle, including protons and neutrons, which make up atomic nuclei. Baryon number is a quantity assigned to particles. Protons and neutrons have a baryon number of +1, while antiprotons and antineutrons have a baryon number of -1.
If baryon number were always absolutely conserved, it would mean that the total baryon number in the universe, matter minus antimatter, would not change. This implies that if the initial amounts of matter and antimatter were equal, they would never become asymmetrical. Therefore, for an excess of matter to exist, there must be physical processes that allow the baryon number to change. The second condition is the violation of charge symmetry, C symmetry, and parity symmetry, CP symmetry. C symmetry implies that the laws of physics remain the same if we replace every particle with its antiparticle. P symmetry relates to the laws of physics remaining unchanged when we observe a physical system in a mirror. CP symmetry is a combination of both, meaning the laws of physics are invariant when we simultaneously replace particles with antiparticles and reverse space, like looking in a mirror. If CP symmetry is violated, it means that certain physical processes would occur slightly differently for matter compared to antimatter. This subtle difference could lead to the creation of slightly more matter than antimatter under certain conditions, or cause antimatter to annihilate faster. Third, these processes must occur under conditions of thermodynamic non-equilibrium. Out-of-equilibrium processes means the universe must expand and cool rapidly enough so that the processes creating the matter excess cannot reverse to an equilibrium state. If the universe maintained thermodynamic equilibrium throughout the period of matter formation, then all reactions would proceed in both directions, creating matter and antimatter at the same rate, and any asymmetry created would be quickly erased. Only when processes occur faster than equilibrium can the matter excess freeze in and persist. Among Sakharov's conditions, CP symmetry violation is an aspect that has been confirmed through laboratory particle physics experiments.
For the first time, CP violation was observed in 1964 in the decay of neutral kaons, K-mesons. Subsequently, experiments with B-mesons conducted at particle accelerators like Babar at Stanford and Bell in Japan provided clearer evidence of more significant CP violation. These experiments showed that matter particles and their antiparticles do not decay entirely symmetrically. There is a small discrepancy in the ratio of decay products. However, this is the crux of the problem. The amount of CP violation observed within the standard model of particle physics is too small to explain the enormous matter-antimatter imbalance we observe in the universe. Theoretical calculations based on the standard model can only produce a matter-excess ratio much smaller than the required 1 in a billion. This indicates that the standard model, while highly successful in describing fundamental particles and forces, is still incomplete. There must be new physics beyond the scope of the standard model to provide sufficient CP violation and other mechanisms necessary for matter formation. So, what could this new physics be? One of the leading candidates is supersymmetry. Supersymmetry proposes that every fundamental particle in the Standard Model has a heavier superpartner. For example, electrons have s electrons, selectrons, quarks have s quarks, squarks, and so on. These supersymmetric particles could interact in ways not allowed by the Standard Model, creating additional and larger sources of CP violation. If they exist, SUSY particles could have played a crucial role in generating the matter excess. However, despite search efforts at CERN's Large Hadron Collider, LHC, experiments so far have not found any direct evidence of these supersymmetric particles. Another increasingly interesting possibility is the theory of heavy neutrinos and a process called leptogenesis. Neutrinos are extremely tiny fundamental particles that interact very weakly with other matter.
The original Standard Model assumed neutrinos were massless, but experiments have proven they do have mass, albeit very small. Leptogenesis theory proposes that if heavier types of neutrinos exist that we haven't yet detected, and if they could decay asymmetrically, violating CP in the early universe, they could have created an asymmetry in the number of leptons, a group of particles including electrons and neutrinos. This lepton asymmetry could then be converted into baryon asymmetry through special processes called sphalerons occurring under the high temperature conditions of the early universe. Scientists are also extensively researching Electroweak baryogenesis, another scenario to explain the asymmetry. This process takes place during an early phase of the universe's history when it cooled enough for the electromagnetic and weak nuclear forces to separate. Under extremely high energy and rapidly dropping temperatures, a phase transition bubble could have formed, creating a dynamic boundary and a non-equilibrium thermodynamic environment. The walls of these bubbles could have created a small difference in the amounts of matter and antimatter, allowing the excess matter to form and persist in certain regions of the universe. Additionally, there are more audacious hypotheses, such as the existence of new scalar fields interacting with the Standard Model in special ways, or even the existence of extra spatial dimensions where physical laws might operate differently. These ideas, though still in the realm of theoretical speculation, show the complexity and diversity of potential solutions to the mystery of excess matter. Unraveling the mystery of excess matter in the universe is not just an interesting academic problem, it holds profound significance for our fundamental understanding of the universe's origin and structure. If we can discover the precise mechanism that led to this asymmetry, it would be a colossal scientific breakthrough, not only strengthening current cosmological models, but also potentially opening the door to an entirely new physical model, a new Standard Model with previously unknown particles and interactions.
Our existence, that of stars, galaxies, and all matter in the universe, is living proof of a miraculous, subtle, and profoundly important event that occurred in the first moments of time. It is a powerful reminder that even the smallest, most subtle discrepancies at the most fundamental level of reality can lead to grand and profound consequences, shaping the entire reality we contemplate and experience today. The journey to find answers continues to drive humanity's relentless scientific exploration. The mystery of matter and antimatter reveals that the universe harbors countless peculiar things where seemingly simple properties carry deep meaning. One of the most fundamental yet elusive properties of particles is spin. It's not physical rotation in the conventional sense, but a form of intrinsic angular momentum that dictates how particles interact and form the structure of matter. In our next video, we will delve into the strange world of spin, exploring the true meaning of this quantum property and how it shapes our universe. Don't miss it.